Every time we go to space, we fight a violent battle against gravity. Modern rockets are essentially massive fuel tanks where over 90% of the total mass is dedicated purely to the propellant needed to lift a tiny fraction of cargo. It is a loud, dangerous, and incredibly expensive process that limits our reach to the stars. But there's another way to leave the planet, one that doesn't involve combustion or explosions. It involves a single, continuous structure stretching from the surface of the Earth into the deep silence of space. This is the space elevator, a concept that could transform the cosmos into a backyard accessible to everyone. The idea isn't as modern as it sounds. In 1895, the Russian scientist Konstantin Tsiolkovsky visited the newly built Eiffel Tower in Paris. He wondered if a tower could be built so high that its top reached into the vacuum of space. While a traditional building would eventually collapse under its own weight, Tsiolkovsky's celestial castle laid the groundwork for a different kind of architecture. He realized that if a structure were tall enough, the outward centrifugal force of Earth's rotation would eventually balance the inward pull of gravity. Instead of building up from the ground, we would effectively be hanging a line down from the sky. To understand how this works, we have to look at geostationary orbit. If you place a satellite approximately 236 miles above the equator, it orbits the Earth at the exact same speed that the planet rotates. To an observer on the ground, the satellite appears to stay perfectly still in the sky. If we were to attach a long, strong cable to a satellite at this height and drop it down to the surface, we would have a permanent physical link between Earth and space. It functions like a giant spinning lasso, kept taut by the physics of orbital motion rather than rigid beams or girders. The physics of the system relies on a delicate balance of forces. Imagine spinning a weight on the end of a string. As long as you keep spinning, the string stays tight. In a space elevator, the Earth is the hand spinning the string, and a massive counterweight, perhaps a captured asteroid, sits at the far end of the cable far beyond geostationary orbit. This counterweight provides the outward pull that keeps the entire 60,000-mile-long tether under tension. The center of mass for the whole system stays at that sweet spot in orbit, meaning the elevator doesn't fall down and it doesn't fly away. While the physics is sound, the engineering presents a monumental hurdle. The tether would need to support its own weight over tens of thousands of miles while resisting the immense tension pulling from both ends. No existing material is strong enough for this. Steel would snap long before it reached the upper atmosphere. Even Kevlar or high-grade carbon fibers fall short. The material must have an incredibly high strength-to-density ratio. This search for the perfect thread has led scientists to the molecular level, where atoms are arranged in perfectly repeating patterns to maximize their collective strength. The most promising candidates are carbon nanotubes and graphene. In a laboratory, these structures are hundreds of times stronger than steel and as light as plastic. Carbon nanotubes are essentially sheets of carbon atoms rolled into perfect cylinders. If we could weave these microscopic tubes into a long, continuous ribbon, we would have a material capable of reaching the stars. The challenge today is scaling up. Currently, we can only grow these tubes a few centimeters long. To build the elevator, we need to find a way to manufacture these high-purity carbon structures by the mile, maintaining their atomic perfection throughout. Instead of a round cable, engineers propose a thin, flat ribbon that is slightly wider at the center than at the ends. This tapered design helps distribute the load more efficiently. Climbing this ribbon would be a specialized vehicle called a climber. Unlike a rocket, which must carry all its energy with it, a climber could be powered from the ground. High-powered lasers located at the base station would beam energy to photovoltaic cells on the underside of the climber, or it could use solar panels as it rises above the cloud layer, slowly and quietly ascending into the vacuum. The base of the elevator would likely be a massive floating platform located in the equatorial Pacific Ocean. A mobile base allows the system to move slightly to avoid extreme weather or space debris. This platform would serve as a global spaceport, a quiet hub where cargo and passengers board the climbers. Because there is no explosive launch, the experience would be smooth and gradual, similar to a high-speed train ride that simply happens to go vertical. Over the course of a few days, the sky would slowly darken from blue to black as the atmosphere thins away. The true impact of the space elevator is economic. Currently, it costs thousands of dollars to send a single kilogram of mass into orbit. This high cost is the primary reason why space remains the domain of governments and billionaires. A space elevator could reduce that cost to roughly $100 per kilogram, or even less. At that price point, space becomes a viable place for industry, large-scale solar power collection, and even tourism. We could build massive structures in orbit using materials brought up from Earth for the price of a standard shipping container. Building a space elevator will be the most ambitious engineering project in human history, perhaps taking decades to complete once the materials are ready. We would likely begin by spooling the cable out from a spacecraft in orbit, slowly lowering it toward the Earth while extending a counterweight in the opposite direction. It is a slow, methodical process of connecting our world to the rest of the solar system. Once the first ribbon is secured, it can be used to carry the materials for a second, stronger ribbon, allowing the structure to grow and reinforce itself over time. The space elevator represents a shift in how we think about our place in the universe. It turns the terrifying hurdle of gravity into a manageable climb. While we are still waiting for material science to catch up with our ambition, the physics tells us that this is not a matter of if, but when. When the first climber finally reaches the geostationary station and the doors open to the stars, the era of the rocket will seem like a primitive, distant memory. We will no longer be visitors to space. We will be part of it, connected by a 22,000-mile thread to our future.
If you'd like more videos like this, you can subscribe and come back to Brief Stories anytime.